Swayam Prabha. Digital India. Educated India.
Welcome back to the final module of our course, module 12 on drainage and recharge, and lecture 56 would be on groundwater recharge, and this is part 1. So, in this particular lecture, the different concepts that would be covered are on need for artificial recharge, artificial recharges, benefit of artificial recharge, and planning for artificial recharge. So, as we have already learnt in our first module, we have discussed about the different groundwater related issues in the Indian context, and we know that in groundwater in India serves around 85% of the rural domestic water demand and approximately 50% of the urban water demand. So, you can understand the role groundwater plays in both urban and rural areas, and without and because of depletion of groundwater, there would be a lot of crisis in the coming days, and that is why we need to consider artificial recharges, or we need to consider recharging of groundwater. So, we already know that about 839 out of around 6,000, approximately 6,000 groundwater blocks, in 2004 it was found that the groundwater extraction is actually more than the net annual recharge. So, that means if groundwater extraction is more than the net annual recharge, so gradually the groundwater table will go down and eventually the aquifer would be depleted. Whereas, another 226 blocks where it was found that extraction is about 90 to 100% of the annual recharge. So, it is almost at similar levels at the first 839 blocks. So, you can understand around 1000 blocks out of total approximately 6,000 blocks are where we are going to face severe shortage of groundwater. Now, this is going to exacerbate further. Why? Because you see in this particular table that I have provided, you see the type of groundwater abstraction structures in India during the year 1982 to 2001, we would see a tremendous growth for all these groundwater abstraction structures, or that means the different structures that are used to take out groundwater. For example, we have dug wells, we have shallow tube wells, we have deep tube wells. So, these are the different equipment or the structures using which we take out groundwater. So, you see their growth. So, like the total number of dug wells during 1982 was around 53 lakhs, whereas it has now increased to 96 lakhs in the year 2001, and now further it must have increased. Then shallow tube well, it was around 4 lakh 59,000, whereas it is right now around 83 lakhs. So, you can understand the number increase. Similarly, for deep tube well, it was only 31,000, whereas it is right now 5 lakh 30,194 deep tube wells. So, you can understand the rate at which we are extracting our groundwater, and it is still, this data is for 2001, and for now it has further increased, and that means that we will have other groundwater blocks also gradually getting their groundwater will gradually deplete as well. So, that is why we need to be very, very concerned. So, what happens with decline in groundwater levels? So, first of all, one is there will be shortage in water supply. That is the first problem. Then in the coastal areas, we will see that there will be intrusion of saline water, because there is no groundwater in the aquifer. So, the saline water will push towards the inward, and we will see that there is intrusion of saline water, and as you know that intrusion of saline water will lead to agriculture, all these things will be affected. Pumping will become costlier. So, the lower the groundwater table goes, our existing pumps will or deep tubules will not be able to get the groundwater, and you have to again put in much more deeper deep tubules, and that will actually increase the cost of abstraction. You have to put in more powerful pumps and so on. So, that is one problem, and the other thing is geogenic contamination of groundwater. That is, we are gradually finding, because we are over abstracting and we are also using groundwater only in some cases, we are seeing that arsenic, fluoride and iron, which are usually in very little quantity in groundwater, but now because we are abstracting too much and we are reaching the lower levels of the aquifer, and probably that is one of the reasons why the quantity of arsenic, fluoride and iron is also increasing in the groundwater. So, these are the different issues that are going to come in the coming days, and already we are facing these issues in many parts of the country. So, that is why artificial recharge is required, and it is the most cost effective method to augment groundwater resources. So, that means instead of a natural recharge, which happens normally because of rainfall or precipitation, and then gradually the water percolates into the soil, but we have to consider artificial recharge to increase that particular rate. And the Central Groundwater Board is the main body in India which actually looks about groundwater abstraction, utilization, and all the different regulations related to groundwater, everything, all the policies are made by this particular body. So, we are seeing that the groundwater is gradually depleting in many of the states, and that is particularly because of indiscriminate abstraction. That means people are putting up deep wells and all, and there is no record of that, and you are drawing groundwater from places where there is no water at all, and this is threatening the sustainability of the entire area. And particularly we are seeing this in some of the states such as Rajasthan, Gujarat, Tamil Nadu, Punjab, Delhi, Haryana and so on. And traditional water harvesting methods that was earlier used, that has been totally abandoned, and that actually people are more groundwater or use of deep wells actually give people an easy way out. That means instead of going for so much going into harvesting of water and so on, it just run a pump, get the water out from the ground, that would be a better solution. So, people are actually so that is creating problem. Then groundwater pollution. So, that is another reason why we need to do artificial recharge. That is, we are having too much application of fertilizers and pesticides, which are gradually going into infiltrating into the groundwater, and plus there is lot of disposal of effluents from the industries and urban sewerage, which is not actually treated, and then that is also reaching the groundwater. And so, this is a big problem, and that means many of the groundwater aquifers are also becoming unusable, or maybe if we use them, then probably that would lead to a lot of diseases. So, that means the type and spread of pollution within the groundwater aquifers also needs to be modeled, studied, and and eventually controlled. So, there has to be a lot of work in that regards as well. So, artificial recharge will actually help in sometimes providing other aquifers, or where there is or giving alternatives to groundwater resources, and which is because the current many of the current aquifers are actually getting polluted and are becoming unusable. Then potable water supply in urban areas is also, as we are discussing, 50% of the water in urban areas are supplied from groundwater sources, and many of the urban complexes, that means this residential large complexes, maybe of 1,000 apartments or maybe 2,000 apartments, they are drawing groundwater because municipal bodies are not able to supply them the quantity of water they require. So, along with municipal bodies, these complexes are also putting in their deep wells and drawing water from the ground, and we are seeing steep decline of this water level, maybe even up to 30 meters. The groundwater table is going down in some of these particular areas where this kind of abstraction is happening. And so, what are the solutions to that? So, one solution could be, if we can instead of taking the groundwater out from those urban areas where already the water table has gone down, instead if we can take the water from floodplains where there is adequate water, and we can put high yield tube wells, and those could be sustained in those particular areas. So, if we can shift the abstraction points, then probably that is we will not create this kind of problems. And then also we can also recycle and reuse of water, and we can use dual water supply systems as we have discussed earlier. Maybe one water supply system just for potable purposes, another for other non-potable purposes. So that will actually we would be able to reuse, and we can treat and then reuse some of the existing wastewater. So that will actually reduce the demand for groundwater. And finally, rainwater harvesting and other measures which also could be introduced, and that for that we require regulatory interventions, monitoring, enforcement, and so on. So then we are seeing seawater intrusion in coastal aquifers because of groundwater abstraction, and artificial recharge actually can prevent that to a certain extent. And what we can do is we can form two things. Either we can form freshwater ridges, or we can pump, using pumping we can create troughs. So ridges are we increase the level of groundwater by recharging it, by artificial recharge, and so that means we are giving that extra water which doesn't allow the saline water to creep in. Whereas the other one, that is pumping, that means wherever saline water is coming in, we create one. We understand which are those aquifers, and we use pumps to pump out those water, or we create troughs before that, and then we pump water out of that, and that will draw groundwater from other sources as well. So that means, these are the two approaches that we actually take for both freshwater ridge formation as well as pumping trough formation. So these two ways we can actually prevent saline water incursion, and we are seeing this in Gujarat, Tamil Nadu, Andhra Pradesh. These are some of the states where saline seawater intrusion is becoming a problem. Then, when we talk about artificial recharge, that means we are trying to replicate the natural recharge, but obviously we want to introduce the rate of the natural this recharge. So both artificial and natural recharge is governed by the same physical law. So that means we put water on the ground and the water percolates inside the ground. So that's the basic physical laws that we follow. But the thing is, we want to increase the amount of water that is available for putting in the ground. So that is what is different in artificial recharge, and that means water has to be made available for artificial recharge, and groundwater is increased at a rate exceeding the natural rate of replenishment. So that is why it is artificial recharge. So there are different engineering techniques to it. So we will discuss that in the next lecture. But broadly, this could be categorized into three methods. One is construction methods. That means we construct certain structures using which we can actually recharge groundwater, maybe some wells and all. Then there could be spreading of water. That means we spread the water over the ground surface, and with some amount of construction of structures as well. And that actually helps give a larger surface for the water to percolate, and or by artificially changing natural conditions, like we create pump troughs, or we create these groundwater ridges. So actually this is like using pumping and all. We change the flow of groundwater in the aquifer, and that actually helps in prevention of maybe intrusion, or maybe it will connect multiple aquifers and bring groundwater to from one aquifer to another. Then two effects. When we talk about groundwater recharge, we have to be aware of two effects. One is these are hydraulic effects generated by artificial recharge. The first effect is the piezometric effect, that is the rise of the piezometric surface. That means the rise of the groundwater table. So that means via groundwater recharge we increase the height of the groundwater table. So this is the first point, and the other is the volumetric effect. That means we increase the specific yield of a particular aquifer. That means we put in groundwater at a certain times of the year. In other times of the year, we are able to take out that water for use. So groundwater is actually being stored. So instead of storing it in an open reservoir, we are storing it inside ground. So that means there is a volumetric effect as well, which that means the specific yield of that particular aquifer is what we are concerned with. And once the groundwater infiltrates, it also distributes, that is in between two infiltrations, the groundwater obviously spread in that particular area. So sometimes we use techniques to actually prevent the spread so that the groundwater is retained in that particular aquifer. So these are sort of groundwater, some call it conservation techniques. And in other cases, we want groundwater to spread from one aquifer to another so that the water is available in both the aquifers. So both techniques are utilized. So in India, as I was explaining just now, that is the rainfall period is roughly 3 months, and artificial recharge will be able to extend this period by another 3 months. But what it means is, that means the amount of infiltration that happens in India is during the 3-month period of rainfall. So we can increase this period by another 3 months by storing that rainfall water on the surface, and or by using certain techniques like spreading or creating some wells, and we can actually gradually put more water into the ground using artificial recharge techniques, and that probably will increase this infiltration time by 3 months. And because it happens for 3 months, and again so because we are extending the infiltration time, the total amount of water that is going into the ground is more, and so we can also increase our rate of abstraction as well as we can or the period of abstraction. That means there would be certain lean periods during which we can take the water out from the ground and we can use it. Now let us see an example. For example, in arid regions of India, the rainfall volume is rainfall intensity is total amount of rainfall is 150 to 600 millimeter per year, and usually we have got only 10 rainy days and maybe 3 to 5 major storms lasting few hours. So you now understand that what does storm duration, then number of stormed events, all these things mean, right? So all of these create hydrographs. That means there is some the water goes into a particular channel or it flows along a particular surface. So we at only at very small time intervals we would be able to some amount of water would be able to percolate. It's not like the water is uniformly available throughout the rainy season for percolating in the ground. Only in certain time periods we will be getting water which will percolate into the ground. And sometimes in this particular arid region, the evapotranspiration rate is so high. That means if we store the water on the surface, then actually it is not feasible to keep it because it will fully evaporate. So there is no point of storing it in the surface by creating surface reservoirs. So that is where groundwater recharge comes in. So subsurface storing of conserved rainfall from these few storms can actually increase the groundwater level in that particular area or the amount of groundwater that percolates in that particular area, and that actually could be utilized in other time periods. And recharge structures actually help in transferring surface storage to the groundwater reservoirs within a short period of time. So that is why we design engineered structures which actually shorten the process of percolation. Similarly, in hilly areas, we have both high rainfall as well as high surface runoff, and in lean periods we see that many of the springs become dry in hilly areas. So in this particular case, maybe small surface reservoirs around the recharge areas of the springs could be created, which actually will help in increasing the groundwater in that particular areas. So now that we are talking about that artificial recharge, and instead of storing the water in the surface, so let us see what are the benefits of artificial recharge. So first of all, there is no need to construct costly storage structure. That means we usually create dams in the river, and we also create large water bodies with lining and all. So we reduce on those particular costs. Why? Because subsurface storage is free and evaporation loss is also minimum. So usually the effectiveness of subsurface storage is much better. So storing the water in the ground is actually better than storing it on the surface. And reservoir storage also have some social impacts like displacement of population and loss of agricultural land. we have seen that whenever a dam is created and then we have created reservoirs where we store the water for other periods of the year. So, we see that a huge area gets flooded and we have to replace those particular people. So, this kind of social impacts are there, which is not there in groundwater this recharge. Groundwater storage of course reduces the inundation, the flood. If we increase infiltration, obviously the floods would be less, and infiltration also improves water quality. So, more amount of water from the rain infiltrates, the water volume increases, and the quality of this water is also better, and reduces soil erosion, flood, and ensures adequate soil moisture even in summer. So, we have already learned that whenever there is more infiltration, the soil will have more moisture, and the flood volume would be less, the soil erosion would be less, and everything in that way it is better. And sometimes costly convenience cost is avoided because we need to transfer water from one if we store it in the surface. If I want to take the water to another area, we have to use pipelines to transfer the water. But if the water is stored in the groundwater, if the hydraulic gradient or the slope of the land is favorable, then probably there is natural or subsurface distribution. That means the water travels below ground from one point to another, and in both places the water will be available. Pumping requirement may be reduced as well. So, these are the different benefits of artificial recharge. And as we know that whenever we are evaluating any kind of projects related with groundwater recharge and all, some of the benefits are going to be tangible and some others will be intangible. We will talk about this later also. And usually the cost benefit analysis for this kind of projects, we need to understand that the quantifiable aspects has to be put in, plus the environmental benefits has to be considered, as well as the social aspects in terms of money, that also needs to be considered. That means all this has to be brought in terms of money, right. So, that means the money saved due to social benefits, money saved from environmental related benefits, and also the quantifiable benefits that we get. Otherwise, it is very, very difficult to justify this kind of projects, right. So, how do we plan for artificial recharge? So, there is a method that we have to follow. It is not like we can just start storing water and allowing it to percolate in the ground. We really need to do proper analysis when we plan for recharge structures in our urban area or in our catchment area. So, the planning could be at different scales, of course. So, we are mostly concerned with the small urban areas, but it could be done at the state or basin level. It could be done at the district or sub-basin level, or block or watershed level, and then again of course, the urban level is also there. So, we can plan for artificial recharge at different levels, different levels of networks of recharge structures could be also conceived. But what are the different steps in this particular process? This is very, very important, and you should learn this at the beginning, that whenever we are talking about recharge, first thing that we need to say is there a need for artificial recharge? Because excess recharging, if we keep on putting water in the ground, eventually it will create floods, right. So, there is no point of putting in water which is not required. So, is there a need for artificial recharge? So, this is the first thing that we have to justify. Second is subsurface storage capacity and water required for recharge, if both is available or not. That means, we are thinking of recharging a particular aquifer, but is there subsurface storage capacity in this particular aquifer? And this is one. The second is there adequate water required for recharge? That means, we will say we will recharge, but is there excess water available to recharge? So, these are the second thing that we need to ascertain. The third thing is, where are we going to recharge? That means, all this artificial recharge that we are planning, at which areas we will do, how we will decide or prioritize certain areas. So, this is the third question. Fourth question is source water availability, both quantity and quality assessment needs to be done, and as you can see, water required for recharge. This is how much water is required for recharge, and this is water available for that, right. So, these are the questions. And then suitability of the recharge area, that means, is the recharge area suitable for recharge? That means, considering climate, topography, soil, land use, hydrogeologic characteristics, is it suitable? Then economic viability of this particular project and the physical plan of that particular project. So, we will learn all these different steps in detail one by one. So, first of all, let us look into the need for artificial recharge. So, why we need to recharge first of all? So, one reason could be to overcome deficit during summer or winter season. So, during the lean periods, we are not having water in that particular area, maybe we want water, so we need to overcome that deficit, right. And the other is to overcome perennial deficits. Like that means every year we are seeing that the groundwater table is going down because of over abstraction. So, we want to make sure that it doesn't goes down every year, and we want to improve upon it. So, that means here the this entire deficit is compounded over years. So, as you understand that recharge just is not adequate, because we are every year it is increasing. So, some amount of additional regulation through legislation is required, which will prevent indiscriminate abstraction in this particular place as well. So, in some places just additional recharge is good enough, because overall the demand and supply could be balanced, whereas for other areas we need to have some amount of prevention of groundwater abstraction, so that those areas this we can overcome these perennial deficits in these particular areas. Then comes the main thing, that is the subsurface. Is there subsurface storage capacity, and how much water is required for recharging that particular aquifer? So, as you understand, like in this particular table, we have got these lines. These lines are contour lines, that you are already aware of contour lines, and but these lines are contour lines for groundwater table. That means at what level this groundwater is available, that is being shown in using these contour lines. So, each line may be at a distance of 1 meter or a difference of 1 meter level of the groundwater, and all the points being connected by a single line have got groundwater at the same levels. So, you can understand, like a normal digital profile of a terrain, like a digital elevation model, this actually gives the elevation of the groundwater levels. So, when we compare two aquifers, and we know that right now the water table is at a particular level, we can actually determine that what is the difference in in between two levels, what is the quantum of water required. So, if I have a area like that, and this is at somewhere the water table is like this, and the other area water table is like this. So, if I want to reach this particular height, what amount of water would be required to put in there? So, we need to compute the area required for this volume of water which has to be put in. So, that is why a contour actually helps, a groundwater contour. So, the subsurface storage capacity depends on the thickness of unsaturated material available above the water table in the confined aquifer. So, that means how much amount of unsaturated material is there above the the groundwater table in that particular unconfined aquifer, that actually determines the area where the water will be stored. Now, depth to water level, that is the reference level during post monsoon period 5 years average, that is the depth of water table that is average for that particular area. So, that means when I say what is the level of water table in that particular area, we will consider the 5-year average for the depth of water table during the post monsoon period. So, that is the level in after normal monsoon season, after normal recharge, what is the level at which the water table is there in that particular area. Then water table contour maps with suitable contour intervals are prepared, and what we determine is the intercontour areas below a certain cutoff level. That means we, as I say, that this is the maybe that reference level, that is this is after monsoon, we find that the groundwater table over here. Then we can say that what is the cutoff level, that let us assume that we want to take groundwater up till this particular level. So, this is the cutoff level. So, in between this intercontour area, how much amount of water could be stored, that is what we are determining. And water is stored in the pores of the soil in that unsaturated material above. So, that means we multiply that with the specific yield of that particular soil. So, you remember specific yield and from porosity, right? We have done this in our water supply classes, and specific yield is actually the water that could be abstracted from a particular layer, and we can multiply that rate with this intercontour volume actually, and that actually will give us the total volume of subsurface storage space available for recharge. So, this is the storage space available for recharge. So, this is where you can store groundwater. So, first we need to create this subsurface storage capacity, we need to determine that. So, this is how we determine that. And why we need to do that? Because if we put in more groundwater than this particular volume, then it will result in waterlogging. So, actual requirement of source water, this is to fill this particular volume of soil is basically depends on the average recharge efficiency of individual structure. That means, if I put 100 liters of water in a recharge structure, based on its efficiency only a percentage of water actually gets into the ground. So, let us assume that 60 to 90% is the efficiency of that particular structure. That it could be made for many reasons. It could be losses of water from evaporation, it could be losses of water, just some amount of water will not percolate, and maybe so many other reasons are there. So, average recharge efficiency of the individual structure is also important. So, that means we need to fill in this amount of volume of surface storage space. This is one. Second is to fill that we have to put in water, but there is a efficiency of that particular recharge structure. So, we have to put in more water than it is required. So, volume of water required for artificial recharge is equal to volume of surface storage space multiplied by reciprocal of recharge efficiency of the structure. So, that is 1 by maybe that 90%. So, that is the reciprocal of that recharge structure. So, in this way we can determine that how much amount of water 100 by, if it is in percent, 100 by 90. So, this is the factor which we need to multiply to get the actual volume of water that would be required. The next job is to determine the areas for recharge. How will we determine where to recharge, and also how do we prioritize between these areas? So, usually we prioritize considering the post monsoon water level maps and long term groundwater trend of groundwater levels as well. So, we use both the values. We see what is the current water level post monsoon, of course, and what are the trends of this level of water in groundwater in that particular area. So, for example, water level at 3 to 6 meter below ground level and declining trend of 0.1 to 0.2 meter per year. That means, every year there is a decline of the water table by 0.1 to 0.2 meter. There is another area where water table level is found to be less than 9 meter below ground level. So, it is 9 meter below ground level, the water table level, and the declining trend is 0.4 meter per year. So, where we will recharge? Obviously, the second one. Why? Because it is going down at a much faster pace, and also the level is also lower. So, areas having deeper water levels and declining water level trends are given much higher priority. Then we have to make sure that source water is available. That means, groundwater is available, and where do we get that means, for recharging this we make sure that there has to be water using which we can do this artificial recharge. So, where do we will get this water? The main water that we will use is precipitation in the watershed area. So, in that particular catchment area or watershed area, we will the precipitation that falls, that is rainfall, and then eventually from that runoff, and all this runoff happens, and we need to capture this and then use it for infiltration, and this is primarily the main source for artificial recharge. Or we can go for nearby streams, springs or aquifer system, and then we can consider seepage from the stream flows that will actually recharge this particular area. So, that could be also a possibility. Then surface water using canals from large reservoirs located in the watershed or through transbasin water transfer. That means, if locally there is no water available, it is a arid region, we need to get water from somewhere else. So, we may use canals to bring in water to that area from some stored reservoirs from other areas, and or from transbasin, and this is also called transbasin water transfer. That means, we are bringing water from other catchments as well. Then treated municipal industrial wastewater, that is also possible. That means, we reuse water, the treated water could be reused for recharge. So, in all these cases, the water that has to be made available for recharge has to be the non-committed surplus runoff and other source of water and its distribution in time and space. So, it has to be non-committed. That means, there is no other use for this water. Only then we will put it for recharge. If already we have estimated that the reused water would go to a thermal power plant. So that means already there is a designated use for that water. So we cannot assume that that reused water will come for recharge. So we need to make sure that there is adequate non-committed surplus runoff and other sources of water in that urban area, and when it is available, it's where it is available. So both time and space is also important, and based on that we determine where the recharge should happen. Based on that we determine that which water should be used for recharge. And quality of source water and pre-treatment required. So that is also another issue. That means because we cannot just put in any water, we have to do some amount of treatment, or we need to check if the water is of good quality, then only we can allow it for recharge. And finally, conveyance system to the proposed recharge site. So the place where the water is available and the recharge site may be far away. So we need to also design a conveyance system to take this particular water. Then we need to check the suitability of the recharge area, and we already talked about these factors, which is climate, topography, soil, land use and hydrogeologic conditions. For example, climate determines the spatial and temporal availability of water for recharge. That means high rainfall area, excess rainfall needs to be stored for recharge. Low rainfall area, water has to be imported from transbasin areas in addition to storage measures for runoff. So this is how that climate of that area actually influences the kind of recharge that we can do in that particular area. Similarly, topography, this topography determines the extent of runoff and retention, and in hilly areas we need to consider water conservation measures such as gully plugging, bench terracing or contour terracing, and this slows down the surface runoff and causes more infiltration. So it's not a simple task. We need to plan for this entire recharge structure of this entire recharge process, that first we need to prevent the water to flow away, then we need to store the water, then we make sure that the water infiltrates into the ground. Soil and land use, similar to topography, soil and land use also plays a big role in determining the extent of infiltration. Depth of soil, texture of soil, mineral composition, organic content determines the infiltration capacity. And then we have the hydrogeologic condition, and the potential aquifer system and the suitability for artificial recharge. So that means the aquifer, nature of the aquifer plays a role in what kind of recharge is possible, how much amount of recharge is possible. In India, we have 3 classifications for this kind of aquifers: consolidated ones, semi-consolidated and non-consolidated formations, which actually influences the amount of recharge that could be done for these aquifers. Then finally we come down to the main points, like everything else is fine, but if it is not economically viable, then there is no point of doing this particular project. So cost benefits of the projects are evaluated. So I was already talking about that earlier, and cost of project includes everything, like cost of the investigation or maybe cost of making the plans, then source water, conveyance treatment, conveyance as well as treatment, that means carrying of the water as well as treatment of that water before recharge, construction of recharge structures, operation and maintenance of that recharge structure. All these things are the cost of this particular project. Whereas the benefits of the projects, as we were discussing earlier, could be environmental benefits, social benefits. So sometimes those could be tradables and sometimes those could be non-tradable items. That means we cannot put monetary cost to them. And then we really need to be careful about determining the cost of a project. So we need to make differences. We need to understand the difference between financial price as well as the economic price. And economic price also includes the opportunity cost as well, right? So that means financial prices are absolute, money numbers, whereas economic prices consider all the different benefits and all the different other costs, or that is there, which we are able to save and which we can also consider in this particular project. So acceptability of project from economic but not from financial point of view is possible, as long as resources are used efficiently, even though with additional financial support. So that means even with more investment than we are getting actual financial benefit, we can still do a project considering the economic prices are within limits, and we can see that the investment that we make will return adequate benefits. Some other points like economic appraisal is decisive for the acceptance of the project. Definitely, without any kind of economic appraisal or a cost benefit analysis, we cannot go ahead with any kind of project. This kind of projects will also contribute to the economy. That means there are some labor and wages for skilled and unskilled workers that we can consider, because these are large scale projects where we can involve a huge amount of people. So that will have influence in the the spreading of the benefits from doing this kind of projects. And then project will we also say that the benefit the project will not consider the final output. So the economic prices are based on the initial conditions, and economic cost should be considered both by the producer and the user. So one who is actually constructing and the one who would get the benefits, both the producer and the user should consider economic cost instead of financial cost. So finally, if a project is financially viable, we need to prepare the physical plan. So the physical plan includes the layout plan showing locations of the proposed structures, conveyance systems, and the source water, and we would use appropriate scale for that. So how many structures are required? Usually we use multiple structures, and location of these particular structures, these are important to put in the map. Then design specifications and engineering drawings, construction and overall project time schedules of the project. So this is construction management related part. Financial planning, sources of fund, allocation required at various stages, schedules of repayment, and identification of agency for executing the scheme. So this part is the hard part, where the engineering part comes in, or the project contract awarding comes in. So these are also part of the overall project, but as planners we can actually justify our project when the economic costs are viable. We can say this is the rough design of the project, and that is where we can end, and then the engineering design team could take over. So what do we need to prepare? So when we propose a particular project, when we make a plan for it, we need to do detailed projects report. So we need to give the background, purpose, scope, technical feasibility, objectives of the project, and layout plans, drawing specifications of structures, execution plans, financial allocations, monitoring systems, and all the details has to be, what we discussed right now has to be provided in the DPR to justify this, or before we start this kind of project. So to conclude, artificial recharge depends on subsurface storage capacity and source water availability and the suitability of the recharge areas. So all this thing needs to be considered before we start any kind of artificial recharge project. And economic appraisal and not financial appraisal is important in deciding the viability of recharge projects. So these are some of the references that you can use. Thank you.